everybody. Gives me my great pleasure to introduce tonight's speaker, Jeff Dunk, who is a local faculty member, has been working in the Department of Environmental Science and Management now for 20 years. And Jeff is at the forefront of all kinds of ecosystem-based models, and he was involved in doing some modeling recently for the northern spotted owl. And Jeff's work is really interesting because it's right on that interface between science and policy, because the work that he's going to be talking to you about today became one of the foundational pieces for the Fish and Wildlife Service's recent draft critical habitat determination for the northern spotted owl. So this is really a good follow-up to Tyrone's talk this morning about how scientists can have a role in management and policy implications, and Jeff is a really good case study of how that's playing out right here in our region. So without further ado, I turn it over to Jeff.
All right. Wow. Thanks for coming, everybody. I appreciate that. 6 o'clock on Saturday. More intellectual nourishment. That's awesome. All right. So I have been involved in this for quite some time, going on 3 years now. But I've been working with a large group of other folks as well, even more than are listed as co-authors here. There's 18 or 20 people that have had fairly significant contributions to this. So I just want to make sure folks know that. It's been a fascinating project to be a part of for me. Like Dominic said, as at this sort of interface between science and policy, and it's been a great learning experience, just really stimulating. So here we go. I didn't think that the title was that catchy, but you're all here, so that's great. Or the abstract, as some of my students have said. It's a pretty long title. So where and how much? When we get into conservation planning and we're trying to figure out where do we put set-asides, where do we put parks, wilderness areas, conservation areas of various types, places that need to be protected for various reasons, how do we actually decide that? And there's a whole process to it. There could be an ad hoc process where we could bring out a bunch of maps and all of us could sit there with Sharpies, start drawing lines on our favorite places or places that we think are really important, untouched places, whatever the criteria might be. We might, according to the conservation planning literature, we would look at what are our goals? What are we trying to accomplish? Are we trying to represent all of biodiversity or the vast majority of it? Viable populations of rare species? Ecosystem processes, these sorts of things. We would then ask, to what extent do current reserve networks take care of those things? To what extent do wilderness areas, national parks, state parks, these sorts of places, late successional reserves for the Forest Service and BLM already take care of these things? And our goal here was to try to figure out where on the landscape we could put critical habitat networks for the northern spotted owl. Something, if you've been around for a while, or even if you haven't, it's been the subject of an awful lot of research. So we're very lucky. We're kind of an embarrassment of riches of data on a species that is very unusual. So we use information like habitat use, habitat selection. Habitat use is just where organisms are. Habitat selection looks at where they are relative to the abundance of that type of habitat in the landscape. Do they disproportionately select some places and away from others? Ideally, we would have information on the effects of selecting particular habitat on survival and reproduction, that is, on fitness of the organisms. And we're also constrained in the real world by law, by policy, by land ownership, economics, and other considerations. So this isn't just on a computer you can ask any question you want and you can do anything. When it gets applied, other factors come into consideration. There's uncertainty, even with this embarrassment of riches of data. There's still uncertainty. We don't know everything. there's a lot of variability out there. So where does the data come from? Is it a snapshot from a small period of time, from a small geographic area, or is it representative of the entire range of the organism or organisms of interest? How do we account for the potential and likely effects of climate change in the near and short term? How do we account for the increasing effects of barred owls, who I'll introduce in a few minutes, in the future? How do we account for potential effects of catastrophic stand replacing fire and those sorts of things? So I'll hit on some of those in the next little bit. So a very brief background of the spotted owl. It was in the news. There were the timber wars. I don't know that we're done with them, but if you were around in the late 80s and early 90s, you know, you'd have boards of supervisors with chainsaws and leading parades and other folks. I mean, it was a pretty contentious. Not that we're all holding hands now. But the owl was listed under the Endangered Species Act as a threatened species in 1990, so it was given some federal protection then. In 1992, the Fish and Wildlife Service designated critical habitat, around 6 million acres of land for the owl. So that's one thing that you'll recognize is critical habitat isn't a fixed thing that just once it's done for good. It's not like a national park's boundary that is fixed. It can be a dynamic thing. It can be expanded or decreased even, and it happens. In 1994, the Northwest Forest Plan was created to sort of try to call a truce to the timber wars. The Clinton administration came in. Environmentalists, scientists, the industry got together, and the Northwest Forest Plan was born as an ecosystem management plan to try to take care of the spotted owl and a whole host of other species, hundreds of all of the other species. In 2008, a recovery plan was published for the northern spotted owl. No recovery plan had been published up to this point, even though the owl was listed in 1990. A draft plan was developed under the first Bush administration. George H.W. Bush, that is. But the Northwest Forest Plan became the de facto recovery plan without an actual recovery plan. 2008, a recovery plan was published, and critical habitat was designated. It was about 5.5 million acres of critical habitat. That plan was immediately, and that critical habitat designation were almost immediately challenged in court. The Obama administration came in and decided not to fight that court challenge and said, we'll do a different one. Okay. In 2011, a different one came out. The recovery plan came out, and it's online if you're interested in reading it. And in 2012, just in March of 2012, what's called a proposed rule, as Dominic mentioned, for critical habitat came out. So the federal process for this sort of thing is to publish a proposed rule, take public comment, respond to public comment, and then come forward with a final rule. So here's what we're telling you we're thinking about doing. What do you think? We're listening to what you're thinking, and here's what we've decided based on that. That's likely to come out in November sometime. There's a court-order deadline for November 15th, so I'm guessing by November 15th. So why was the owl listed, and what has changed since that initial listing in 1990? Well, habitat. Habitat loss was the primary reason that the northern spotted owl was listed. It's largely, or it's affiliated with and it does better in older forests and areas with older forest conditions. And those were disappearing and had disappeared fairly rapidly, especially after World War II and through the 1980s. An emphasis on harvesting on public lands reduced an awful lot of their habitat. And their populations were declining. It wasn't just we saw habitat disappearing. There was pretty good evidence that populations throughout the range were declining significantly. Habitat's still an issue. That's the one thing with habitat, especially when we're talking about coniferous forest. You can go one way really fast. That is, you can reduce its extent really quickly, but you have to wait an awful long time for it to come back, right? We can eradicate a lot of habitat in a decade, but if you just wait another decade, it's still not there. Okay, so even if you arrest the decline, the expectation of a response by organisms who need that is shouldn't have been made because it takes a while for habitat to grow back. In contrast, for things like bald eagles and peregrine falcons, we just stopped putting DDT out. Habitat was there. They came back when the poison started to dissipate. So, the barred owl has emerged as a significant issue in the last, we knew about it 15 years ago, but in the last 10 years, it's really become a significant thing. And I'm going to show a graphic here from a paper that was just published in the journal Ecology. And here we go. So in the upper left is it's a study area in the Oregon Coast Range. The black spots are areas where they detected barred owls, and this is 1990. This is 2010. This study it's one of the demographic study areas. There's about 11 of them throughout the owl's range, the northern spotted owl's range, and it just gives you kind of a time series of how the barred owl has come into and expanded its range. It started north in northern Washington and has sort of moved into Oregon and now Northern California. Barred owls are in the same genus as spotted owls. They're competitively dominant. They're a little bit bigger. They're not as focused or specific in their food habits. They eat a wider variety of things, and they just basically are out-competing spotted owls. There's probably a little bit of direct mortality, but in some cases, and Lowell Diller, who works around here with Green Diamond, and others have done some fairly simple removals, only to find that the spotted owls come right back when the barred owls are removed. But the barred owls sometimes are going in and just taking up the exact same nest sites that the spotted owls had. It's not just a similar place. Sometimes it's the exact same place. Okay. So that's a new thing. It's a new stressor that's been brought into the system since the owl is listed. So here's a subset of the guiding principles we used for designating critical habitat. I shouldn't say that. For looking at what we looked at, I had nothing to do with designating it, actually. That's a policy decision, and I'm not a politician. But we wanted to ensure sufficient habitats to support population viability across the entire range. It's possible that you could have a viable population in Northern California and Southern Oregon. That wasn't what they were after. It was throughout the entire range of the species. How big is the entire range? It's about 50 million acres, 20 million hectares. Habitat will be sufficient to ensure a low risk of extinction in each recovery unit. So there's a whole series of recovery units throughout the range. We don't want extinction in any of them, or a low likelihood of extinction. We certainly don't want it. We want to conserve and enhance connectivity within and among recovery units. There's one region up in the Olympic Peninsula that is very isolated, and all of our work shows that, but also so does all of the empirical work, all the work on the ground. Ensure sufficient spatial redundancy in critical habitat within each recovery unit. The idea isn't to say, how little can we get away with, and then something happens like a wildfire, and like, whoops, well, if we only had that piece that disappeared or became unsuitable because of climate change in 20 years, now it's going down. We want to have a margin of error there. Ensure the distribution of owl populations across representative habitats. We want them everywhere that they've occurred, and across the full ecological gradient of their historic range. We did incorporate uncertainty to some extent, to the extent that we could, in terms of barred owls, climate change, fire and risk, and demographic stochasticity. That term will be on the test for me. So here's the outline of the process. I'm going to bring this figure back several times, but this is the fun part. It is. So we wanted to characterize the suitability of habitat throughout the entire range of the species, and we used a species distribution model called MAXENT. It's a maximum entropy model. That's a nice word too, but it uses presence-only data. A lot of modeling is done if you have presence and absence. MAXENT allows you to evaluate habitat suitability with just presence locations, which is nice. We used that base MAXENT habitat suitability map and imported that into a conservation planning algorithm called zonation. Both of these are free and online, by the way, if you're interested. And zonation, basically, I'll talk about it in more detail, but it amalgamates things to pieces of the landscape, or it could use the seascape as well, into sort of blocks of reasonably sized areas, as opposed to Maxent was done on the base map we used was a 30-meter resolution. So we had 30-meter pixels across 50 million acres. You're not going to be setting aside critical habitat units that are 30 meters on an edge. And then, so we had a whole series of zonation scenarios, different potential critical habitat networks, and we subjected those networks to a variety of scenarios with habitat change and scenarios with barred owl change. So I'm going to talk about two things throughout this. One is networks. Networks refer to potential critical habitat networks. Scenarios refer to changes in habitat and changes in barred owl influences. Okay? And then we ran those through the fancy name HEXIM, our individual-based spatially explicit population model, and looked at what the outcome for the owls was of a particular network by scenario. Okay? And we iteratively went through a whole bunch of this, and I'll talk about that. Not everyone. You're welcome. And then, you know, we started talking to policymakers. Hey, are you guys ready? What do you think? And we sent them a bunch of ideas, and then it goes to this political process where the scientists can do stuff, and then the political process takes over with folks from the Fish and Wildlife Service and the Department of Interior, not to mention folks in Congress, I'm sure. There we go. All right, so here we go. Habitat suitability modeling. First thing we did was we broke the geographic range of the owl into 11 distinct areas because owls don't use habitat the same everywhere. They use the habitat quite differently, actually, in the Redwood Coast than in most of the rest of the range. But this allowed us to be a little more nuanced. So we had 11 different modeling regions, and we created these models in each of the regions. There was a whole bunch of data that we had available to us because owls have been fairly well surveyed over time because they've been threatened and because you can't jeopardize a threatened species. If a federal agency wants to do something in potential habitat, they often have to survey for them. Okay? So we had available to us about 3,700 site locations, nest sites or roosting sites throughout the range on private and public lands. And here's how they're distributed amongst the various modeling regions. We used about 2,800 of those. We thinned the 3,700 locations so that they weren't right next to each other, so we didn't double count the same bird that might have a different nest the next year that's, half a kilometer away and call that the same place. So anyway, so we had a lot of data. How do we develop the models? Well, there's a really rich published peer-reviewed literature on spotted owl habitat selection. We definitely leaned on that. We reviewed every paper that was published. We went around to experts, biologists who work for tribes, private companies, or federal or state governments throughout the range. We went out and chatted with them and asked what was going on in their area. And we had a fair amount of experience as well, our team did. So we developed a whole series of models, potential models for each of the 11 modeling regions. And in the end, we applied the best model to the landscape and then knitted them all together. They were developed at a 200 hectare scale. So the data occur at a 30-meter pixel. But we went out 800 meters from that and said, what's the condition of the landscape around that point? And there's a lot of evidence that owls select nest sites at that scale. So we used a 200 hectare scale, not just what's the condition of that 30-meter pixel, what's its condition and everything else around it. We use biotic information from some remotely sensed data that are called the generalized nearest neighbor. They're from Janet Oman and her colleagues at the PNW Research Lab in Corvallis, and a whole series of abiotic variables. So if you're into GIS, you'd like this. So we built the models and we evaluated them using something called the area under the receiver operating characteristic curve. So a lot of neat words to throw around at dinner after this. And that's really an evaluation metric that looks at the ability of the model to discriminate between areas where the owls exist, where they selected, and the background random locations in the environment. And gain is another metric, and it looks at the average difference between where the owls were and the random points in the landscape. Interestingly, not interestingly maybe, but it is interesting, and importantly, we built the models with 1996 data because first we had the GNN data from 1996, but secondly, the barred owl's influence throughout the spotted owl's range was much more reduced in 1996 than it was more recently. So we built the models before the barred owls became a huge impact, when they were a moderate impact, and then applied those models to more current time, 2006. That was the bookend period where we had the GNN data. So modeling is fun, but you can fall in love with what you create, right? You have to, how good is it? You're always going to come up with something. So we do something called cross-validation, where you take subsets of the data out, create the model without those subsets, recalibrate the model, and then classify the withheld data. We withheld 25%, recalibrated the model with 75%, classified the withheld 25%, did that 10 times within each modeling region. And it gives you an idea of how robust the model is. Is it just a house of cards that if you perturb that data set at all, it just falls apart? Or is it fairly robust to perturbations in that developmental data? Which is what you want. You want a robust model that has usefulness not just for the data that it went into developing it, but you want to apply it to novel circumstances. Okay. For some regions, we had independent data as well. Independent data is like the gold standard in science, right? Develop a model with one set of data and apply it to another, and if it works there or it works in several other independent data sets, we love that. So, like I said, it's an evaluation of how robust the models are. And I'll talk about this, but there's a bunch of acronyms, but I won't be testing you guys, don't worry. So, the distribution of relative habitat suitability. Here, this is the state of Washington. These bluer and magenta colors are high suitability areas. The brown is kind of low, moderate, and white is poor. Okay? So you can see in the state of Washington, not chock full of high quality spotted owl habitat, somewhat rare, according to our model. State of Oregon, Western Cascades is pretty nice. The Willamette Valley, not a lot there. We're not too surprised by that. And there's a little bit in the Oregon Coast Range, and then here's California. California actually, it turns out, has more high suitability owl habitat than either Oregon or Washington. And then here's the entire range put together. Okay. So this was the base information that we fed into our conservation planning algorithm. And just some of the quick results here. The AUCs, these values, you can read. The maximum potential value is 1. Okay, a value of 0.879 means that 87.9% of the time, if you took a random sample of an owl location, we had hundreds of them, and a random location, the owl location would have a higher suitability value 87.9% of the time. So this is the discrimination metric. Good discrimination, basically across the board, which is wonderful. That's what we wanted. And here's just a histogram showing you the distribution of habitat suitability in various classes. I put them into 7 different classes here. And they're going from the modeling regions that have the most low suitability habitat to the least low suitability habitat. So here's West Cascades North. About 73% of that place is made up of habitat that has very little value to spotted owls. Okay? And very little of it is made up of really high suitability habitat. And I'm not going to walk through, I'll put the histograms up, but this is the redwood. I used red. Yeah, but very little of the redwood region is made up of low suitability habitat. Okay? And this, remember earlier I said that owls use the world differently in the redwood region. They do fairly well in areas with timber harvesting in the redwood region. That isn't replicated elsewhere through their range. So there's a lot of medium and even a reasonable amount of fairly high suitability habitat in the redwood region, also in the Klamath West, the Klamath East, and interior California coast. But the take-home message here is that most areas have a lot of low suitability habitat. No areas have a lot of high suitability habitat. Okay. And then this is our what's called the strength of selection, and it gets to something that's called model calibration, and it represents the extent to which owls disproportionately are attracted to or stay away from areas with these various habitat suitability values. So up here, owls are using this high suitability bin about 12 times more than you'd expect based on the extent of that area in the landscape. They're using this low suitability area about 12 times less than you'd expect based on its extent. So they're not using this stuff very much, and they're using this stuff almost always. Okay? And then there's intermediate, right? So it gives you an idea of the sort of relative, the degree to which owls disproportionately use these areas. And this is what you want. This is a well-calibrated model, should have a cline going from not using the bad stuff very much to using the intermediate stuff an intermediate amount of time to using the good stuff a lot of the time. That's what you want. Okay? So it's just another evaluation metric. So in our cross-validation tests within each of the 11 modeling regions, there was very little difference between the full model and the cross-validated model. So the full models were quite representative, it turns out. The difference was 1.6% to 4.5% in terms of the categorization of the habitat within each modeling region. And then here's the independent data we had and trying to characterize the distribution of habitat suitability with the training data, which is the 1996 data, and independent data. We had almost 1,000 locations. Not a whole lot of difference here. We're seeing the same general pattern. This gives us a little more security that both cross-validated and independent data are telling us the same thing. Good. We like that. And thus, I'll continue. So conservation planning. So how do we take that and come up with alternative networks? And this program, zonation, is very powerful, but it's quite simple. It's made for looking at multi-species data. So you could, Carlos Carroll and I and a guy named Ate Molanan, who developed this software, did this for 130 different species simultaneously, and looking at where would be an optimal place to put reserves for those 130 species over a few different climate change scenarios. We used it here for only a single species, the owl. In zonation, what it does is it basically, like I said earlier, it amalgamates areas into conservation-sized units. That's not its real intention, but it does, and I'll show you how it does that. But for each species you're looking at, only one for us, you tell it how big is the species home range and how easily can the organism get around. So an owl can get around the landscape quite easily compared to a mollusk or a salamander, right? So, if I'm on a piece of habitat on this platform and I'm a salamander, something in the other room, it may as well be on another continent. I just can't get there. There's nothing between me and it, and forget it. If I'm an owl, it's nothing. I'm going to be there in a second. I'm there. It's connected. Okay. So it's that sort of thing where you look at the organism's vigility, its ability to get around the landscape, and how big of its home range is. Okay. You can prioritize lands. You can tell it we have to put in all of the federal reserve lands first, or you can't consider private lands, or you can consider everything, but first put in only public lands, and then if you can't meet your goals, then we'll start adding other lands. You can consider cost. If you were a nonprofit and looking at, acquiring lands, you might say, boy, I'm not going to pay, $50,000 an acre for some of this stuff. It's off the table to begin with compared to stuff that's $800 an acre, something like that. So it allows for these sorts of things to be put in up front if you want. So sort of a little bit more economic and political realism can be built in. And here's just a transition from the left side is the maxent surface for a piece of our study area, and the right side is just starting to put things together with zonation, right? These are blocks that you might be able to, yes, that place, you know, it could be critical habitat as opposed to a whole bunch of little 30-meter pixels. So good habitat that's isolated is going to rank lower in zonation than that same high-quality habitat, good habitat, that's next to a bunch of other good habitat. So, and I'm putting up two circles here. You can see that blue piece right there, and it's right there too. There's all this other bluish purple stuff that gets, that zonation selects, and it selects a whole bunch over here too. But this isolated piece, it doesn't. It has the same habitat suitability as a lot of places that were, but it's too isolated, and so it wasn't selected by zonation in this iteration of it. So anyway, so we can go through, and zonation gives you something called the habitat value. It goes through and it'll rank every single pixel, every single 30-meter pixel in 50 million acres. It's a lot. Okay, so it'll rank every one, and it starts by including everything and sequentially removing the lowest suitability, and then the next lowest suitability, then the next lowest, until the last thing. You know, so it starts up here, and the last one that it removes is the highest suitability pixel, the highest ranking pixel. So this curve shows, you know, the proportion of the total landscape, the proportion of 50 million acres or so, and the proportion of habitat value. And luckily, hopefully you'll understand why, it's not a straight line, right? You can start shedding a lot of area without losing a proportional amount of habitat value. Sorry. So we can go from here to here, let's say right there, what do we got? We're at 60% of that 50 million acres, and you still got 90% of the habitat value. You've lost 30% of the area, but only 10% of the value. Okay, that's kind of nice. All right. This is a depiction if there's no restriction on what's included. Public, private, tribal, doesn't matter, everything's fair game. This is a depiction of if the decision was, it's only federal, nothing else, we can't use anything else. And if we used all the federal land, it's just under half of the landscape, and it's got about 62% of the total habitat value. If we only use the existing reserves on federal lands, it's about 30% of the landscape, and we get about 39% of the habitat value. Okay? So we could have told zonation these things to begin with, but I'm just trying to explain how it works with any criteria that you might give it, like can't use or must use. Okay. So, in our phase one, we did 3 phases. We're in the middle of phase 4. We used the Northwest Forest Plan, the existing reserve network, and 6 zonation scenarios. And we called them zonation 30, 50, and 70. 30, 50, and 70% of the habitat value. We did that with a priority on public lands. Get that 30, 50, or 70% of value on public lands if you can. If you can't, then you can go onto private lands. And the other was 30 and 50 and 70% of habitat value on any lands. Okay, there's no restriction. Okay, one of them's much more efficient. If you can go to any lands, you can get a certain amount of habitat value on less area. All right. Phase 2, we did what we called composite scenarios, where we looked within each of the modeling regions at how the owls performed under zonation 30, 50, and 70, public and all, and the Northwest Forest Plan. And we started mixing and matching, saying, hey, they did pretty well here in zonation 50, public. They didn't do well here unless it was zonation 70. They did okay in another area in the Northwest Forest Plan Reserve. So we started mixing and matching. Those are the composites we used. Not one size fits all. And then phase 3, we went away, not completely from the computer's help, but there's other information out there. There's areas where we know there's owls that didn't show up here. There's little pockets in Marin County where there's a population, and we thought, hey, that's pretty important. And there's areas that the models identified that biologists looked at, and they said, gosh, there's nothing there. We've surveyed that area. So and then there was sort of snapping boundaries too, to real ownership boundaries. So, you know, if you're 300 meters into a private land, maybe it's okay to snap that boundary over to the public ownership. There's those sorts of things where people went through it. I wasn't one of those people, and came up with these phase 3 composites. All right. So then we have these scenarios and with barred owls and habitat. There's a lot of process here. There's some products I'll share with you, though. So HexSim, a population model. It's spatially explicit and individual based. So, you know, if you've had a general ecology class, you know about population models like exponential growth, right? Right? I mean, that's nice. We love that one. N sub t is equal to e to the RT, or n sub 0 times e to the RT. Sweet. I just finished it. All right? It's easy. It's just there's some average rates. We apply it to everybody. We do it once. We're done. This talk's over. It's not over. So here, it's individual based. Every owl is accounted for throughout time, not just averaging everything. Every owl in the landscape is accounted for. It's spatially explicit that its vital rates, its birth and death rates, are a function of where it is on the landscape and the suitability of the habitat where it is. They disperse. They die. They have babies. So we were able to program some realism in. So the 3 models, Maxent, Zonation, HexSim, all free, all online. Okay, that's nice. Didn't matter for us, but it was nice. It was cheaper. It mattered. It allows for the interface with a dynamic landscape. You can slot in a changing landscape. You could simulate the effects of wildfire. You could simulate trees increasing in suitability, habitat increasing or decreasing. That's nice. For any amount of time you want. You could run this for 10,000 years if you wanted. And I don't mean the computer processing time, simulation years. It incorporates multiple stressors. Like we could build up the barred owl effect over time. We could introduce a disease. We didn't. I'll tell you why we didn't do certain things. We can. It's individual based, but we pay attention, and HexSim pays attention to individuals that you're born, and you have a particular probability as a newbie this year of living to see your first birthday, and you have a higher probability of living to see your second birthday if you were able to live to your first birthday, right? So we have age-specific birth and death rates. We get all sorts of neat outputs. You can watch movies of what's going on here, I guess, if you're really bored. But you could watch dispersal movies of where every individual goes in the environment and then watch them blink out as they keep trying to get to areas that just happen to be too far away. It's general and flexible. So HexSim is a general spatially explicit individual-based model. We happen to tweak it for spotted owls, but it could be used for fruit flies, it could be used for gophers, it could be used for plants, you name it. That pretty much is everything: fruit flies, owls, and gophers, plants. Okay, why hexagons? Hexagons are space filling. When you have a landscape and you can have a wall-to-wall coverage with no blank spots with a hexagon, you can do that with squares too, but with hexagons, the center-to-center distance is always the same. With squares, it's not. Okay? See, geometry's coming in. That's great. So we use this HexSim to ask, what's the relative impact on spotted owl populations if barred owl encounter rates increase or decrease over time? If habitat suitability increases or decreases, and does so differentially inside and outside of these networks that we looked at. So one of the reasons why you protect areas is to, well, protect them from the forces that threaten them, right? So we would assume that something different might happen inside than outside of critical habitat. What's the effect of designating critical habitat in a particular spatial arrangement? A whole bunch of little places, a few big places, stacked towards the south end, the middle part, or the north end of the range, those sorts of things. And it allows us a consistent way, even if there's errors in this, and there certainly are. It's a model. It's a depiction of, not a complete representation of reality, right? But it allowed us a formal way to compare alternative networks and scenarios and rank their effectiveness, their simulated effectiveness. I realize that. So building realism, we took advantage of this tremendous amount of data. A few of you know about spotted owls. I see Rob back there. But there's been studies on spotted owls in some areas for 20 and 25 years, every single year in multiple places from Oregon, Washington, and California. So it's a huge demographic data set on birth and death rates over time. It's incredible. For most species that most of us work on, you're like, oh, there's 12 locations where it exists. You're like, okay, that's the best I have. Here, birth and death rates over 25 years, nice. We have good information on birth rates by age class. We have good information on death rates or survival rates, dispersal distances, home range sizes that vary from north to south by a factor of 3 or 4 times bigger, 5 times bigger sometimes in northern Washington than here on the coast in California. We accounted for all of that in our model. The influence of barn owls varies significantly. That first shot that I showed you on the Oregon Coast Range, the probability of a spotted owl that is nesting, encountering a barn owl there is 0.7, 70% chance. Here in the Redwood Zone, at least of a couple of years ago, when the data were evaluated, it was about 0.2. Okay? That's a lot of variation from a 20% chance to a 70% chance, and it's variable throughout the range. And we accounted for that. So here's the simplistic version of HexSim. We created this hexagonal network. We overlaid it with our relative habitat suitability map, and we just threw out 10,000 owls, way more than the landscape can handle. But we wanted to fill up the suitable habitat soon, rather than have the Adam and Eve owl take 4,000 years to fill up the simulated landscape. We didn't call them the Adam and Eve owl, but it's going to be on TV now. Anyway, the owls have stopping rules. We used empirical information to tell the simulated birds where to stop. What suitability does that habitat have to be before you can put a nest on it? And we used our 4,000 animals to tell us what those rules should be, and how big their territory should be. So each individual stopped at a particular place and started building a territory. Had a discrete, it built a home range. The territories they had were about 240 hectares in our model, but the home ranges varied dramatically across the range. If an owl settled, there was a determination of whether or not there was a barred owl there, and that probability was a function of the empirical estimates, somewhere between around 0.2 and 0.7, depending on where you were. Survival was determined. Are you going to live to be a year older or not? Reproduction happens. Are you going to have a baby? If so, how many? It's a probabilistic event. If you had a baby, that baby's going to disperse. And then they're going to look for a place to set up for breeding. And then we can insert different barred owl changes. We could simulate a reducing barred owls, increasing barred owls, holding them steady. So we can insert those whenever we want. We can insert habitat changes as well. And then those will influence the stopping rules. So this allowed for competition. Birds could share part of their home ranges, but not their territories. And then if that happened, they would split the resource value from those home ranges. And we would run the model for 250 or 350 time steps. That's the language we use, because it's simulated years, and we don't want people to come away thinking, oh, here's what's going to happen 250 years. We don't think that at all. Okay, we did not try to what's called hindcast and represent all of the changes that have happened on the landscape in the last 200 years. We just started it with the current landscape and then put changes into the future, but we don't think that what we get in 250 years means 250 years from now. That's just an important point. And then we evaluated the output, which we're about to do. Here's really what we did. Just kidding, that was that crazy Pentagon slide for Afghanistan or something. That's my point of reference for, do I have too much information on a slide? And the answer has always been no for me. So what we didn't do, we didn't include mate finding. We didn't evaluate barred owls as a spatially explicit thing. It was on a modeling region by modeling region. We didn't evaluate genetic issues, that when you get a really small population and there's more likelihood of inbreeding, HexM will allow for that. We just didn't have empirical evidence to do that. There's the Owlee effect, mate finding, right? If there's two individuals in 1 million acres, a male and a female, there's a very low likelihood of them finding each other. We assumed if you set up a territory, you found a mate. Okay, so there's some, those are some of our assumptions. Prey, we didn't evaluate them. And here's what we like to say. We attempted to utilize the best information and stick with what we knew well, and generally only if we had reasonable estimates throughout a large portion of the owl's range. So complex to the point that it was valid to be complex. But if we couldn't lean on data, we didn't. We didn't use it. So some data, some results. Does HexM give us some decent results? So here's these white bars are density estimates from the ground, from a bunch of these demographic study areas, right? How many animals they found, mean of the 3 highest years over 15 to 25 years that they've been surveying. Here's what HexM estimated would be on those same places after time step 50 with barred owls. So this one we're not that happy with, this one we're not that happy with, but overall, yeah, we're pretty happy. These, we're not expecting perfection, a depiction of not an exact representation of the world. So dispersal, this is an interesting one too. So here on the dark line is Eric Forsman published a bunch of dispersal stuff from 370 or so female owls, and this is how they dispersed over various distances. And this is 850,000 simulated owls dispersing. Pretty close to, nothing crazy going on there. So these are sort of things, sort of checks for how is this thing doing? Again, it's always going to give you an answer and you can fall in love with it, but how real is that? Okay. So we're feeling pretty good about this being a reasonable representation. So here's the scenarios we looked at. We isolated the reserves, or the networks. So we kept their habitat suitability and we reduced it everywhere that wasn't in critical habitat to a suitability value that wouldn't allow for owls to breed, for nesting. They could use that area, it would contribute to a home range, but they couldn't nest there. So this was complete reliance on a reserve, basically, for nesting. HAB2 was kind of like HAB1, except we kept high suitability habitat that wasn't included in the network on public lands. HAB3 was we kept it on public and non-public lands. We have something called the optimistic scenario, where there's very few changes in habitat suitability over time, and a pessimistic one, which is basically HAB1. And these are the ones that decisions were made off of. The first 3 were sort of these course level evaluations, and I'm going to share some of those with you in a minute. The barred owl scenarios we looked at, one that's completely unrealistic, no barred owls in the landscape. But it's a nice point of reference for the potential of what spotted owls could do with the habitat that's on the landscape. It just seems extraordinarily unlikely. If you're a betting person, don't bet on that one. Barred owls held constant at their currently held encounter probabilities, held constant at an encounter probability of 0.25, which is a pretty big reduction in most areas, or held constant at an encounter probability of 0.5. The 2 highest current encounter probabilities throughout the range are 0.71 and 0.505. So those are high. The others are 0.3, 0.2s. And then we put a ceiling. This is the last thing we did. We put a ceiling on barred owl encounter probabilities, and I'll share some reasons why. But after we did our initial evaluations, if you had a barred owl encounter probability at 0.5, habitat didn't matter. The barred owl effect was overwhelming. Okay, so we had to make an assumption here, or in the simulation, that some management would happen to hold barred owl populations lower than they are now, and hold them steady-ish at that lower level. Okay. All right. So if you're interested in numbers, we looked initially in phase 1 at 7 different networks under 3 habitat change scenarios, 4 barred owl scenarios. That's 84 network by scenarios. In phases 2 and 3, we looked at 8 different networks, only with optimistic and pessimistic, and with our ceiling barred owl scenario. Okay, and we ran those. We had 100 replicates there. We included environmental stochasticity. Phase 4, I have questions there because we're in the middle of that right now. All right. So what did we look at? The number of years the population was stable or increasing. First year it was stable. Percent of the population change over time. Pseudo-extinction thresholds, just sort of worry levels that, hey, if it gets below here, it could be in trouble, like from genetic issues, the allele effect. And what proportion of the simulations did the population go extinct, both modeling region-wide and range-wide. After that core scale stuff, we looked at very similar things, but total population size on the last time step, percent of simulations that met some pseudo-extinction thresholds in modeling regions and range-wide, and total extinction likelihood. So just to give you an idea of how big of an areas we're talking about, over here, the Northwest Forest Plan, 6.65 million hectares, so 16 million acres or so. And I just showed some of these big ones here. So Z30 all is 3 million hectares. If you're not into hectares, it's 2.47 acres per hectare. 10 million, that's 25 million acres for Z70 pub. And then this was the one, I circled this because Comp 7 was the one that went to the proposed rule in late March for getting public comment. And that's about, it's not about, it's 13.9 million acres. Doesn't include other congressional reserves, wilderness areas, parks, places like that Congress has set aside. So here's another 2 million acres of congressional reserve that we didn't identify as critical habitat, or as potential critical habitat. Careful. You want to know the impacts of the barred owl? Here's what they are in our simulations. So what the metric here is the percentage of the time step 50 population that's realized at time step 250. So this first one right here, the Northwest Forest Plan, if there's no barred owls in the landscape, the difference is that at time step 250, the population's at 95% of what it was at time step 50, only a 5% reduction. Z70 all, it increased by 3%, okay? And across the board, if we go horizontally here, not much change. If there's no barred owls, big areas, small areas, yeah, owls are doing pretty good. And this is our HAB3, which is truncate, except keep high suitability on all lands. And also, if we assume the barred owl is at a 0.5 encounter probability everywhere, it's at 0.5 and 0.7 in 2 modeling regions now, and it's growing in other places. Populations decline significantly from 91% to 87% between time step 50 and 250. Okay, so those are the 2 bookends of what if there's no barred owls and what if there's a lot of them. Okay, and then if they're at an intermediate level, where they are right now in some places, then we see more signal in the reserve network, right? The Northwest Forest Plan sees a reduction of about 36%, but Z70 sees a reduction of about 16% in the population over time. Okay, so if everything's great, very little difference. If everything's horrible, very little difference in the performance. If things are intermediate, then we start to see more signal. Extinction never occurred range-wide in our phase 1, 84 different evaluations, but it occurred in some modeling regions. Okay? Even under relatively optimistic barred owl and habitat scenarios. Pseudo-extinction thresholds were met regularly in some of the modeling regions, and in general, the Northwest Forest Plan performed more poorly than zonation. And bigger zonation scenarios performed, or networks performed better than smaller ones. All right, so we got all that stuff, and then we started this iterative process of composites. I'm just about done too. So here's kind of what some of the data look like, you know, when you're running the population size over time. You drop 10,000 of them in there, they start to decline, and then you throw barred owls in there, and they start to decline a lot more. And we're really interested in what's going on down in here after, once things reach a relatively steady state. So here's differences between the optimistic and pessimistic scenarios for the Northwest Forest Plan and 7 composite scenarios. So the pessimistic is heavy reliance on the network. Okay, you don't allow breeding to happen on non-network areas. Well, these two, the Northwest Forest Plan and Comp 2, didn't do too well. They were significantly different both from each other and all of the others. But otherwise, these other comps did okay relative to each other. All worse than if there's more habitat out there. Did we really do all this to learn this? Well, to some extent. Some of the modeling regions, they're in tough shape. They're in tough shape because of barred owls, and there's just not a lot of habitat there. So the West Cascades North, West Cascades Central, and the North Coast Olympics performed very poorly. Owls went extinct in 75 to 86% of the simulations there. That means it's probably a high likelihood of extinction in those areas. Not that they can't be rescued over time with colonists from other areas, but it's without more habitat and without a reduction in barred owls, they're in trouble in some areas. The interior California coast, Klamath East and Klamath West, absolutely perform the best. They're absolutely the heart, and the West Cascades South are the heart of the owl's distribution right now, and are really kind of holding it up. No extinctions and largest populations. And just, this is my second to last slide, I think. So here's the ending populations in the Northwest Forest Plan, 2,088 to 3,390. That's a pretty big difference. Reductions in the population, a 70% reduction, 30% of its time step 50 population to a 50% reduction. There's a lot of variation there. And then we look at things like pseudo-extinction thresholds, 43 to 10 or 11 to 0. So we're seeing a fair amount of signal here in terms of differences between and amongst these various networks. And one of the things that you might not be surprised to hear is that folks like to be efficient, right? We want the best value for the least amount of input. We want the best response, but not with all of the land. How much land can we put aside and get meet the recovery objectives? Okay. So this is what we're looking at here is the population size here, plus or minus 95% confidence interval versus network size. And the reason why they went forward with Comp 7 was it met the goals, but it wasn't as big. Okay. But I will add, the last iteration of critical habitat in 2008 was 5.5 million acres. The first iteration in 1992 was about 6.5 million acres. This is 13.9. Okay. Proposed. And now it's in this process. Well, we're still working on those phase 4s, but there's a lot of public policy stuff happening where Congress people, the Department of Interior, Fish and Wildlife Service is deliberating. Office of Management and Budget, right? There's an economic analysis of the effects of this, which is really something as well. So, fun stuff. Synthesizing information using these models allowed us to do a repeatable process and to compare amongst multiple alternative scenarios and networks. The OWL is beautifully suited for this because of the rich amount of data that was available on it. We can provide the tools, scientists can, and a whole bunch of what-if scenarios. And other folks can provide those too. Hey, can you evaluate what if this were the case? Sure. Then we enter this public policy political process where choices are made. You know, people are weighing different things. And we're in the midst of that right now. Like I said, a whole bunch of other people participated in this, even more than these folks. Thanks a lot for coming, and I'll be happy to answer any questions. And if you do have questions, I've been asked to ask you to go to the microphone.
Hey, Jeff, since I introduced you, now I get to ask you a question. Could you go back to the second to the last slide?
Here?
Keep going. Keep going, right there.
Okay.
This, to me, is where the policy rubber meets the road. And, first of all, thank you for the exceptional work. I mean, when we were on the recovery team, when I was on the recovery team 5 or 6 years ago, we were asking for this. So it's great that you've been able to pull it together. It's an exceptional product. What happens with it in the policy arena is what troubles me. And when you look at this, it sends the signal that the Northwest Forest Plan is not doing the job. And so anytime you send that signal, it opens the floodgates for scaling back protection. And so you and I talked a little bit about this outside. Part of the reason why you got Comp 7 higher than the Northwest Forest Plan is because the thresholds for habitat, relative habitat suitability in the model were set at the top end of habitat. So you're going after the best habitat out there. The Northwest Forest Plan doesn't do that. It's more of a comprehensive ecosystem-based approach. If you actually set the thresholds at all suitable habitat instead of all maximum or habitat high quality, you might have gotten a different response. I bet you would have gotten a different response. The second thing that I want you to comment on is, as you were forecasting forward in time and looking at the extinction probabilities, what were you doing to the habitat in the model over time? Were you looking at harvest rates? And why is fire being treated as a loss? There's a meta-analysis that Monica Bond and a bunch of other folks are doing now on the 3 subspecies of owls. And it's showing that owls are resilient to fire, yet the Fish and Wildlife Service keeps treating fire as a threat. And so if you put fire into the model as a habitat loss, but the owls are showing up in burned landscapes, there's a problem in terms of whether the model is really predicting reality. So I wanted you to comment on those two. One is a policy implication, or actually both of them are,
okay.
And the second one is, a projection on habitat.
Okay, you might have to remind me of those. So there were no real thresholds that we put in. Every pixel was available to enter. There wasn't, you don't get to enter this network unless you have a value of X. But the way that zonation works, it does end up, it starts by removing the worst. Okay, so that's, I think the reason why the Northwest Forest Plan doesn't appear to perform as well as what Comp 7 does is we absolutely high graded. Right? I mean, the Northwest Forest Plan first, it was an awesome piece of work. They didn't have these tools available, right? And it's multi-species. This is single species. So I think, and there's data, as you know. There's data that say that owls within the Northwest Forest Plan and public lands are doing way better than owls outside of it, right? They're declining they're still declining, but at a lower rate. So we didn't have a threshold that said only high suitability, but we did get most of the high suitability stuff. But there's a lot of intermediate and even some low suitability stuff that shows up in these networks. That's one thing. The fire. So we made no assumptions the service may, but in terms of our modeling, we made no assumptions about the effect of fire. We started with the current landscape. At time step 60, we introduced changes to our relative habitat suitability. So when we went to pessimistic, we did that in 20-year time periods. So we started at time step 60, and then again at 80, and then we held it constant. Okay, my personal opinion on fire is, if owls are doing the best in the Klamath West, interior California coast, and Klamath East, those are fire-prone landscapes. There's some resilience to fire, a lot of it, and certainly fire doesn't erase habitat most of the time, right? It's low intensity as opposed to stand replacing stuff. A lot of the area that was incorporated into these networks I'm sure was historically, all of it was probably historically had been burned multiple times through wildfires. So we didn't make that assumption that fire is always and everywhere a negative thing or has a deleterious effect. But some of the language in the proposed rule suggests that. And I think that in the final rule, I haven't read it. They haven't shared it with me yet. That may change to, they do want to reduce the likelihood of a stand replacing event in high suitability habitat. So hopefully I addressed both of those.
Can I ask you a quick follow-up?
Well, there's a big line there, but okay.
Yeah.
Okay.
What do you think happens to Comp 7 if you subtract off 6 million acres, which is the current proposal now? In the draft rule, it says, we could exempt up to 6 million acres in private and state forests of high suitability habitat. What happens to those?
Yeah. Not the policy guy, but I'll talk. So the question was, what would happen? In the proposed rule, there was potential for categorical exemptions. That is, if we have the right to exempt private land, we have the right to exempt tribal land, we have the right to exempt congressional reserves from critical habitat. That's the total of about 6 million acres that Dominic's mentioning. My understanding of it was, if they were going to do that, the rationale behind it would be because it was going to be used in a way consistent with the way critical habitat would be used, that exempting those wouldn't predispose a different land use, that it would be under they were assuming it would have the same land use. Exempting wilderness areas, well, wilderness areas aren't areas that we're worried about really in terms of losing habitat, or parks, private lands with HCPs, specific to owls, those sorts of things. That was the rationale for it. So, yeah, if we had a different assumption and said exempt those and then truncate their values to a lower thing, it would absolutely have an effect. Okay.
Sounds like he needs to buy you a really nice dinner so you guys can talk about this.
Okay, anybody
I
else?
actually had a really smart teacher once tell me that all models are useful, but none of them are accurate. So don't, take everything word for word. Anyhow, speaking of one of your graphs, I was actually curious about the dispersal distance that you had in the males and females, and
No,
I was just kind of unclear.
They're all females, but
Oh, they were all females that you were talking about there? I guess I just really didn't get what that graph was and what you were trying to explain. If you could, yeah, thank you.
Okay, well, I was trying to get to the point of how much should we believe the model, right? So we have model output, and then we have real information on how far owls have dispersed, and the dark bar or the dark line is from hundreds, almost 400 female owls that have dispersed throughout Oregon mostly, and then the hatched line is dispersal distances from simulated owls in HEXM only. And I was trying to make the point that, yeah, maybe if you were wearing swim goggles, you'd go, those are pretty close, or close enough to not have us go, that seems really unrealistic. We have birds, for instance, we didn't, but if we had birds that were dispersing 500 kilometers and no one had ever found that, we didn't have that sort of thing happen. So that's what I was trying to get at, is just try to calibrating the model with the real world. Okay.
Hi, I'm concerned with the limitations that you put on the barred owl encounters and how that affected your scenarios. The data you used was from 2006. Is that concerned?
Well, no, the data for the barred owls was up to 2008. It was the recent Forsman et al. Meta-analysis, but it came out in 2011, but the data ended in 2008.
Right. And in the past 3 to 5 years, there's places here in Northern California that have barred owl populations that have gone up exponentially.
Yep.
And places where now the encounter probability probably is above 0.5 and up to 0.7. And how does that affect the plan the way it is written now?
Yeah, good question. And we've heard that from a whole bunch of the demographic study area folks and other biologists from parks and forests and industry. It doesn't affect anything that we've done other than the difference between the ceiling that we put on and the current reality, right? So we said, oh, we're going to put a ceiling on, basically we didn't allow barred owl encounter rates to exceed 0.375 because the original phase 1 work showed anything above that, there's a high probability of extinction in that region. So the language in the proposed rule was habitat is necessary, but alone not sufficient without doing something with the barred owl. So that's critical habitat is simply identifying those areas on the landscape that are critical, but it doesn't mean that area alone and just designating it takes care of things, especially when there's another stressor like the barred owl, or I don't know, if there was pesticides or a poison. Yes, they need their habitat, but we also need to stop that other thing that's driving the population down.
So for a loaded question, if all of your models went to extinction at higher levels, wouldn't that state that perhaps this spotted owl should be now listed as endangered rather than threatened? In your opinion.
In my opinion. Thank you. Maybe. That's a policy question, and those, as I'm sure you know, what's the threshold for endangered? Likely to go extinct. And the threshold for threatened is likely to become endangered throughout all or significant portion of its range. Not quantitative criteria, but given barred owls, and I heard a rumor that there was a petition to reevaluate the owl's current status as threatened, and that petition, I believe, said, and it should be endangered, not it should be unlisted. So I think that's on the table now. Somebody who's closer to it than me just answered that. Oh, yeah. Okay. Andrew?
Hi, my name is Andrew Orhosky. I'm with EPIC, and we actually did file a petition in August to uplist the spotted owl federally as an endangered species now, and also to list it in California because it's never been protected in California.
Under California state law?
Exactly.
Okay. Yeah.
The question I had, though, for you, and I have to say this is an incredible amount of work, and I'm looking forward to learning more about it. But under the critical habitat evaluation, the statute requires that you look at both occupied habitat as well as unoccupied habitat. And just so that I'm clear, the model that you looked at was primarily based on habitats that were currently occupied, correct? Because there's large gaps, for example, in southwestern Washington and the Coast Range of Oregon, which likely had a significant amount of suitable habitat at one time, but doesn't now and hasn't for a while.
Okay, so our results, the habitat suitability modeling was based on data from occupancy, from nesting and roosting sites, but it also gave a suitability value to every single place on the landscape. So places that had very similar characteristics to nesting and roosting sites were identified at potentially very high suitability. But I believe, and you probably have more expertise on this than me, but I believe that the policy says, for critical habitat, says that it's habitat that was occupied at the time of listing or something like that. So I think they're trying to get away from, and I don't know this, but if you're doing something for grizzly bears, like lower 48, right? That was their historic range. But at the time of listing in the 1970s, they occurred in Montana and Wyoming. So we're not looking at the entire lower 48. But for us, it wasn't just looking at current occupancy, but Comp 7, by the way, incorporated about 85% of all known locations of the owl. So, locations from 1996 to current. Yeah. Well, yeah. I mean, not necessarily. Certainly, we wouldn't have if it was harvested in the 60s or something like that. Sure. And we did not look at potential, like what happens if you grow habitat, and that could be done. It becomes much more complex for reasons that we can talk about later, maybe. Yeah.
Great presentation, by the way.
Thanks, Joel.
I'm I'm just wondering, how is climate change incorporated into your model?
Okay, climate change was not directly incorporated. But when I did mention climate change, right, that we wanted it to be resilient to those effects. And so we tried to guard against having, this is the edge of the cliff, just that amount of habitat. And if anything happens, the population goes extinct. But if you're just on this side of it, it doesn't. So that's where the spatial redundancy in habitat, well distributed throughout its range, and all of that were attempts to try to moderate against things that we could look at in some way, but it becomes a little bit more complex. Just like if we were to try to model tree growth over time, it's because we're using things like mean tree diameter and canopy cover. What's that? So yeah, you could consider it like somewhat spatial buffers. Yeah. It could be done, but this was fairly complex as it was. Those questions and this, like what would happen if we grew habitat for 75 years in southwestern Washington? That's another 2 years. I'll be back to you. Interesting stuff, though. And we did set up a framework that could facilitate that. So. Others? Had enough? All right. Thanks for coming.